So lesson 2, I called it Freebody Diagrams. This is going to be the single most useful tool that I give you this unit. So last unit, our approach frequently was what we called DFIC, list your data, find a formula, insert crunch. This unit, we're actually going to be, some of you will like this, drawing pictures, drawing diagrams. They're called Freebody Diagrams. I'm going to spend lots of time showing you how to do these. If you do these right, the actual physics becomes fairly straightforward, fairly plug and chug. But we got to get there. Recall, though, I said Newton's second law, really the main equation for this whole unit, F equals ma. So what's some stuff that we can do? Example 1, a spacecraft has a mass of 3.25 times 10 to the 4th kilograms. Its engine can exert a thrust force of 7.25 times 10 to the 4th newtons. At what rate will the spacecraft accelerate? Okay. What's this question want me to find? Wants me to find the acceleration. I'll write down A equals question mark. That's nice. I normally might say, hey, do I know V final? Do I know V? I don't know any of that. In fact, in this case, what they've told me is my overall force is 7.25 times 10 to the 4th newtons. And they've told me that my mass is 3.25 times 10 to the 4th kilograms. So in this case, I'm kind of looking for an equation, I guess, that has F, M, and A in it. Oh, F equals ma. So what am I trying to find, Mark? Can you get the acceleration by itself in that fancy schmancy equation? Yep. So the acceleration of this spacecraft is going to be 7.25 times 10 to the 4th newtons all over 3.25 times 10 to the 4th. Again, this is a chance for you to find or recall where your scientific notation button is. This is the time to get out your calculator and try this yourself, all of you. So on your calculator, hey, what is this? Yep. You get 2.23, and I think I'm going to 3 sig figs here, so 2.23 meters per second squared. Not a very big acceleration. 1 g is 9.8. So this is about a quarter of a g, roughly. Okay, if the spacecraft maintains this constant acceleration for, now I wrote 24 seconds, and in hindsight I said, you know what, that's terrible because there's almost no change. So can you add, instead of 24, make it 240 seconds? 4 minutes, if you do 60 seconds times 4. So if it maintains this acceleration for 4 minutes, for 240 seconds before shutting off the engine, oh, and its initial velocity was 5.6 times 10 to the 3rd, what will the final velocity be? So now we got a nice little review of last unit. What are they asking me to find here? Let's write down, hey, V final equals. Oh, and they told me V initial. That was 5.6 times 10 to the 3rd. And they told me time was 240. Oh, and what did I find in part A? A, no pun intended. So I know the acceleration is 2.23. Hey, have I got something that's got VF, VI, A, and T in it? And conveniently, the VF is even by itself already. So it's going to be, what was VI? 5.6 times 10 to the 3rd plus 2.23 times 240. 5.6 times 10 to the 3rd plus 2.23 times 240. Did I type that right? 5.6, scientific notation button 3, that looks right. You get, I guess, 6.1 times 10 to the third? So even a small acceleration, Taylor, as long as you keep accelerating, you'll keep going faster and 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 faster. You have an unbalanced force. That's Newton's first law. You got an unbalanced force, you must accelerate. Which means, really, if time is not an issue, we currently have the technology to get to the nearest star. We could just set up some kind of a nuclear engine that had about a 40,000-year nuclear cell, and it would exert a small acceleration, but it would keep going faster and faster and faster. It would just take about 50,000 years or so to get to that star. We can do it. In fact, the Voyager probes, which have left our solar system, I don't think they're accelerating anymore. I think they're just coasting. But in about 25 to 30,000 years, I think they will be getting to our nearest star. I don't plan on being around to find out, but it's kind of cool. How far will the spacecraft travel during the, Mr. Dueck, 240 seconds? Oh, I guess now they want me to find that. I'm looking for an equation that has a d in it and some other stuff, because it looks like I have v final, v initial, t, and I have every possible thing I need. So I can use any equation that has a d in it. Hey, let's pick one that already has the d by itself. Sure, let's use our good old d equals vit plus a half at squared. The distance the spacecraft will have traveled is going to be 5.6 times 10 to the 3, 240, plus 0.5, 2.23, 240 squared. Again, if you have not practiced typing this in, I saw a few of you asking your neighbor, hey, where's my scientific notation button? I won't help you on a quiz or a test. This is your chance to find it. In other words, get your calculator out and make sure you know where it is, right? For most of you, it's going to be a button along the bottom row that says exp, or times 10 to the. Some of you, if you have a TI, it'll be a button called EE, and it's probably right above the 7. It might be a shift button. 5.6 times 10 to the third times 240 plus 0.5 times 2.23 times 240 squared. Double check. That looks good. That looks good. A half a t squared. Do you get that? Comma 1.4 times 10 to the 1, 2, 3, 4, 5, 6 meters. Or 1,400 kilometers. Okay, that's moving pretty good. In 4 minutes, that's covering about what? What quarter of the way across Canada? Moving pretty good. Is that okay? Now, cross that out, cross that out. So cross out 48 seconds and 60 seconds because I added it to 240 seconds. But here's my question. So it says in part B, if the spacecraft maintains its acceleration for 240 seconds, and then what does it do? It turns off its engine. So here's my question. What's its velocity after 1,000 seconds? This is Newton's first law. In outer space, once you turn off your engine, unlike on Earth where there's friction, do you slow down? No. Do you speed up? No. You keep going at a steady speed. So after 1,000 seconds, since it turned its engine off after 4 minutes, you know what its velocity is? Its velocity is still whatever v final was. It's still 6.1 times 10 to the third meters per second. Oh, and after an hour, Jake, you know what the velocity is in outer space? Still 6.1 times 10 to the third. The only way you can change it is to have some kind of an acceleration, some kind of an outside force. And in outer space, the two outside forces are your engines or some kind of planet with gravity. Sorry, some kind of star or some kind of astronomical body that has gravity, I should say. Because it could be a star, could be a black hole, could be other stuff. And again, this is why I went on my Sir Isaac Newton little love rant there. He was able to envision outer space in the late 1500s. Gotta give him credit. So, another nice example of Newton's first law. Put your pencils down. So that was a quick review of the last day. You missed more cool videos like that. So, free body diagrams. Hey, what am I going to use in an abbreviation for free body diagram? FBDs. Okay? A free body diagram is a sketch. It's a picture that represents the object that you're analyzing with a dot at its center of mass, which this year is always just going to be at its center. So we represent whatever object, truck, plane, block, car, whatever, we're going to represent it as a dot. And then using arrows, we're going to label any forces acting on the dot, and we're going to figure out what forces are missing by using Newton's laws. Oh, and the length of the arrows will be roughly in scale. In other words, if I want to show that one force is bigger than another force, I'll draw that arrow longer. If I want to show that two forces are identical, Taylor, I'll eyeball it, but I'll try and draw those two arrows the same length. Okay? Let me show you. It's easier to show you what I mean. Example 1 says, draw a free body diagram for the following masses hanging from a rope. So we have two 12-kilogram masses hanging from a rope. One of them is the one on the left just standing still. The one on the right apparently is accelerating upwards at 2 meters per second squared. You with me? All right. So if I'm drawing a free body diagram for the one on the left, what I will do is I will represent the mass with a dot. And then I will say to myself, what are the forces acting on this mass? Get the obvious one. And by get the obvious one, I mean it's sitting on the Earth. What's the force acting on all of you right now? Gravity. So I always draw an arrow pointing down. Gravity. I call it FG. Now, the situation we're talking about, by the way, if you look up, is this, right here, except imagine a 12-kilogram mass. So imagine this. What's its acceleration? So I'm going to ask it this way. Is this accelerating downwards in free fall? Everybody say no. Is it accelerating upwards? Everybody say no. So if the net force is 0, this diagram right now is impossible because that diagram would have to be accelerating downwards because there's an unbalanced force downwards. The fact that it's not tells me there must be exactly the same size force, about like that, upwards. Has to be. Otherwise, Newton's first law wouldn't be right. And we're going to give that force a name. It's the rope. We're going to say whenever it's a rope, we're going to call it tension, capital T. Come on. My pen has been acting up all week. Tension. Okay. Compare that with the right-hand side here. So now we have the same situation, except in this case, we have it accelerating up. Not going up at a constant speed, speeding up, going up. Can you use your imagination? I can't really do that one here. I don't have long enough arms. So what are the forces acting on this block here? Get the obvious ones. Gravity down. Oh. Is this object in free fall? No. So there must be a force acting in the opposite direction. Is the force acting in the opposite direction bigger, smaller, or the same size as gravity? How can you figure it out? Mark, which way is it accelerating? That must mean there must be a bigger unbalanced force up. I would draw tension and I would really exaggerate it so that when I'm doing the math later, I know that's a bigger force. Probably isn't that much bigger, but this is a sketch. What we're interested in is same size or bigger or smaller, not really worried about scale. This is a free body diagram. And you're going to be doing gazillions of these. And they'll get easy as you get practice. But I always, if I'm on the Earth, Zach, start out with the obvious one because that tells me a lot of what the other forces have to be. And the obvious one is going to be gravity. Some types of forces. So one of the forces that you're most acquainted with is the force of gravity. This is the force of the Earth's mass that it exerts on you. Force of gravity is calculated as follows. First of all, F equals what? What's our equation that we've been using so far? F equals ma, but we have a special symbol that we've been using for the acceleration due to gravity. We often write it like this, mg, where g is what? Yeah, which is what? 9.8. Okay? In fact, Alex, from now on, I'm not going to write FG. From now on, actually, I'm even just going to go I'm going to put the equation there. In fact, you saw me. I started to do that on the last one and crossed it up, so I didn't want to scare you guys. But get the obvious one. I'm just going to write mg most of the time. Okay? Oh, what was the other word for gravity that we mentioned last day? The other word for the force of gravity. This is important, so you probably want to put a little star next to this. What was the word for the, not mass, what was the word for the force of gravity? Weight. Which is EI, by the way, because it's I before E except after C, or when sounded as A as in neighbor and sleigh, and weight. Weight is a unit of force. It's measured in newtons, not kilograms. Our society does it wrong. If you say my weight is 65 kilograms, no, your mass is 65 kilograms. Your weight is whatever 65 times 9.8 is. Or if you're doing it in your head, 65 times 10. Your weight is around 650 newtons, a little less. So find the weight. That means find the mg of a 35 kilogram object A on the Earth and B on the moon. Because the mass doesn't change. Mass is related to how much matter an object has. That's not going to change. Well, on the Earth, it's going to be mg of the Earth. It's going to be 35 times 9.8. (35 times 9.8), 343 newtons. That same 35 kilogram mass on the moon, it's going to be mg, but we're going to use g of the moon. I'll call that gm for moon. It's going to be 35 times, what did I say g on the moon was? 1.6. This is why objects feel lighter on the moon or appear to fall slower on the moon, not because their mass has changed, because the force pulling them down to the planetary body that you're standing on has changed. 35 times 1.6, 56 newtons? 56 newtons. Turn the page. Turn your brain on. Here is the fundamental strategy we're going to be using for the rest of this unit. If you, Dom, wrap your brain around this, if I do my job right, everything for the next couple of weeks, you're going to say, oh, that makes sense. I didn't think of it, but now that you've pointed it out, it's pretty obvious. Okay? We're going to be solving force problems, force questions. And what we're going to do is we're going to use a tug-of-war analogy. You all know what a tug-of-war is, when two people are pulling on a rope? We're going to draw a good free body diagram. We're going to label all the forces. We'll figure out any ones that are missing using Newton's laws. And then we're going to use our knowledge of physics to decide which force is the winning force, which force is the strongest force. And we'll figure that out by saying, hey, which way is it accelerating? That's going to be the direction of the winner. Or then we're going to use the following equation. Winner minus loser equals the net force, F net. Where the net force is actually always just going to be ma. That's where the ma is going to show up. The left-hand side of our equation, Taylor, is going to have all sorts of complicated, it's actually not too bad, but it's going to be equal to the net force. It's going to be equal to ma. Now here's what this means. The reason we're doing this, Mark, is last unit, it was much more convenient to always let down be negative and up be positive. This unit, we're going to be looking eventually at this situation. Look up. Where one mass is moving up and the other mass is moving down. It's going to try and always let down be positive and up be negative, Sabrina, is going to get yucky because you're going to have masses moving in both directions. Or we also always let to the left be negative, last unit, and to the right be positive. What are we going to have if we have a situation like, I got to think this through for you guys. Like, hard to do, Mr. Dueck. Like this, where this mass is moving down negative, but this mass is moving to the right positive. Yeah. So here's what we're going to say. For this unit, that 9.8, and you may already have noticed it, Olivia, is not going to be negative. I'm not going to be putting a negative in for the 9.8. I'm going to decide the direction ahead of time by deciding who's winning, and if I do my job correctly, that will take care of all of the signs. I'll add the direction after. I won't need to include negatives or anything like that. If it's negative, it'll be a loser, and I'll end up putting a minus sign in front of it because I'll be going winner minus loser. It's going to be much easier, trust me, and especially if you get to physics 12, you'll go, oh, yeah, holy smokes, yeah, because there we'll have like 3 or 4 different objects moving around in different directions. Yeah. As an example, same one we did a little while ago. It says find the tension in the rope. Okay? Tension is a force. So what does it want me to find, Brad? Tension. You know what? This is a job for a free body diagram. Just like last unit would have been defect, this is our job for a free body diagram, our first strategy. So we're going to represent the mass of the block with a dot. What are the forces acting on that block? Get the obvious one. So I'm going to draw mg down. You'll notice I'm not writing FG anymore. I'm already putting the equation there. Is this block standing still or moving at a constant speed? No. So if it was, then I would draw the same size force up because Newton's first law says my net force has to be 0. Is this block in free fall? So there must be another force up. Which way is it accelerating, up or down? Let me say that again. What direction is winning, up or down? Up. So a longer, bigger force up, and we're calling that tension because it's a rope. Those are the 2 forces acting on any object that's ever hanging from a rope. It's going to be tension and gravity. Who's winning? Tension. So my template is going to be this. Winner minus loser equals F net. Now, we're going to write this in our notes a couple of times, but eventually, Dro, we'll just do the winner minus loser template in our head, and we'll go straight to the forces. Who's winning? Who's losing? What's in the opposite direction of tension? Is there any forces in the opposite direction of tension? Those are losers! Oh, sorry, that came out a little strong at you. Who's losing? And that's going to equal, what did I say F net was always going to be replaced with? MA. In a couple of examples, we'll jump straight to this line without writing the tug of war above it. Okay, Brad, what does this question want me to find? Which is what in my equation? What letter? T. Hey, how did I get the T by itself? Really? Hey, this is actually a far less complicated equation than some of the stuff we were dealing with last unit, isn't it? Because you said that kind of casually and obviously. I agree with you. Tension is going to be MA plus MG. Do I know the, let's walk through the right-hand side. Do I know the mass? Do I know A? 2. Do I know the mass again? Yeah. Do I know G? Not negative. We took care of the negative with our tug-of-war analogy. Grant, what's G? Just plain old? Okay, so tension is going to be 12 times 2 plus 12 times 9.8. Can I do this in my head? It's going to be 12 times 10.8, which is going to be 120 plus 128.4? No, I'm way off. I forgot to carry something. Too many decimals. 12 times 2 plus 12 times 9.8. 141 points, 142, let's say. 142 what? It's a force. Units. It's a force. Newtons. Okay. Same question, but this time, instead of accelerating something up like we're pulling up on the rope, this time it looks like we're lowering something down because I'm looking at the acceleration little vector there. Okay. What does it want me to find? Tension. This is a job for a free body diagram. What are the forces acting on the block? Get the obvious one. Is this object in free fall? How do I know it can't be in free fall? If it was in free fall, what would it say next to the letter A? It would say A equals what? 9.8. So is this object in free fall? Nope. So there must be a force acting up. Now the question is, what force? Tension, because it's a rope. Am I going to draw tension bigger, smaller, or the same size as gravity? Which way is this object accelerating? So who's winning? Gravity. I'm going to exaggerate that. I'm going to draw, oh, that's terrible. My pen didn't work very well. I'm going to draw tension really short. Who's winning? Winner. Minus. Who's losing? Equals my net force, MA. What's this question want me to find? It wants you to find mg? I don't think so. I think example 3, it says find the what? Okay, tension. Now, how would I get the t by itself? What's in front of the t? The easiest way to do this one is to do 2 steps. The easiest way, I think, is to plus this to that side, and at the same time, move this one to that side. How would I move the MA to the other side? Carly, minus it. I'm going to get this. Gravity minus MA equals tension. Is that okay? Do I know everything to find tension? Yeah, I do. It's going to be 12 times 9.8. Why not negative? I took care of the direction with my winner minus loser. I don't need to worry about that for this unit. Minus 12 times 4.2. You get 67.2? 67.2 what? Newtons. Take a look at these 2 situations where you are raising something or lowering something. So here's tension when you're causing something to accelerate up. Here's tension when you're causing something to accelerate down. When is a rope more likely to break? When you're causing something to raise up, or when you're lowering something? Convince me. Oh, because in both of them, I start with, oh, by the way, what if I was just holding the rope still? What if there was no acceleration? If there was a 0 there, what would tension work out to? Just plain old mg, right? And if there was a 0 here, what would tension work out to? Just plain old mg. So that's kind of our starting point. But when you're raising something up, can you see you're adding to mg? You're increasing tension. When you're lowering something down, can you see you're subtracting from mg? You're lowering tension. I don't know if you have ever pulled on a rope, but I'm telling you, it's much more likely to break when you're lifting something up than when you're lowering something down. That may seem obvious, but there's the physics behind it. There's the physics behind it. Example 4. Find the tension in the rope if the mass is moving up at a constant speed. You know what? I probably would underline that phrase there. It's fairly important. Of 3.8 meters per second. Okay. Dom, what does this question want me to find? Oh, very good, very good. You know what? I'm going to start out by drawing a good free body diagram. So here's my mass. What are the forces acting on it? Get the obvious one. Okay, so I got gravity down. Is this mass in free fall? So Newton's first says there must be a force up. Tension. How big? Well, it says it's moving up. So I probably would be tempted to draw tension a bit bigger because it's moving up. Technically, those of you who are really paying attention may notice I think I've made a mistake, but the nice thing about my tug of war method is even if I make a mistake, as long as I'm reasonably careful, I'll catch my mistake. Who's winning? Which way is this thing moving? So what would you be likely to pick, Dro, as your winner? Gravity or tension? So you're going to say winner minus loser, tension minus gravity equals ma? What did I underline? What's constant speed tell you? Ah, I can actually go... In fact, my equation is actually tension minus mg equals 0. Or, rewrite that. Tension equals mg. You know what? It's a tie. If I was being really fussy, what I should have done is drawn my arrow about the same length as mg. I see it now. So just because you're moving upwards doesn't necessarily mean you're accelerating upwards. It's the acceleration that causes an unbalanced force, not the movement. Not the movement. 12 times 9.8, 12 times 10 is 120. 118 point, no, what is it? 117.6. So I'll go 118 newtons. I usually go to 3 sig figs when in doubt. Or technically I should go to 2 and say it's 120 newtons, but no. Parachuting. Mr. Dueck jumps out of a plane. Eventually I jumped out of an airplane. Once he pulls his parachute, air drag has a force of 745 newtons. What's his net acceleration? I think we should represent Mr. Dueck with a dot. What are the forces acting on Mr. Dueck? Get the obvious one. What else? I think I mentioned it in this question. Air drag. Which way would air drag be pointing, be acting when I pull a parachute out, do you think? Brad, up? Should I draw it bigger, smaller, or the same size as gravity? You know what? I can cheat and quickly find out because gravity is going to be mg. Oh, you know what? How big is air drag? Should I draw it bigger, smaller, or the same size as gravity? I'll call it F air. Just made that up. Who's winning? Winner minus, who's loser? Air drag. That equals, by the way, what's this question asking me to find? How would I get the A by itself? Are you starting to clue in why we did all that formula manipulation last time, by the way? How did I get the A by itself? Just divide the whole thing by m. The acceleration is going to be mg minus air drag all over the mass. 92, 9.8 minus 745 all over 92. What is my net acceleration at this moment in time? What do we get? Oh, is there more than one number on the top, Chris? So what are you going to do around the top? What are you going to put around the top? Brackets? Okay, so if I'm typing this in, it's going to be bracket 92 times 9.8 minus 745. How about the 9 in front of the 8, Mr. Dueck? Close bracket. Divided by, Chris, is there more than one number on the bottom? So do I need brackets on the bottom? You could, but that's a waste. 1.7. 1.7, what? Direction. Who's winning? Direction down. See how we're putting it all together? By the way, if this continued, I would die because I would keep speeding up and speeding up and speeding up and speeding up and speeding up, and I'd hit the ground at a deadly velocity. But this is why we don't look at air resistance too much in high school. It's very complicated. As soon as I start to speed up, what happens to air resistance, to air drag? It actually gets bigger. You may have noticed, stick your hand outside of a car sometime, and you'll notice the faster you go, the bigger the force you feel pushing your hand back. Air resistance is a very complicated force. Oh, and as soon as air resistance got bigger, what would happen to my speed? What would happen to my acceleration? And what would happen to air resistance? Now it gets smaller. But then I would start to speed up. What would happen? This is air resistance. To analyze it properly, you really need calculus. You really need calculus. Regan, I guess I wrote this when I was teaching him, jumps from a 4.5 meter high cliff into a lake. Assuming his mass is 65 kilograms, A, find how long it takes until he hits the water. What's A asking me to find? Time? Okay, I can do that. And you know what? I think because of that, I just moved into last unit, my distance, velocity, acceleration, where down is always negative unit. What else do I know? Don't tell me it's 4.5, because it's not. What? Oh yeah, he's ending up below from where he started from. Oh, he's jumping. What else do I know then? I know A is what? Now I'll include the negative. We're back to last unit, where down was always negative. Oh, and when you jump or when you drop, what else do you know? I know VI is 0. You could argue that when you jump off of a cliff, you do jump up a tiny bit. Let's keep it simple. Let's just assume you stepped off the cliff, because keep the math nice. Hey, I'm looking for an equation that has T, D, A, and VI in it. Although, could I have done this? Why could I have done that? VI is 0? Okay. I'll bring that back because I just terrified some of you, but I'll cross it out. So we have this. D equals a half AT squared. What are we trying to get by itself? Okay. Ready, Brad, my friend? Let's get the T. The T by itself. The D is going to stay where it is, right? Do I care about the 1? No. What's the 2 doing? It's on the bottom, so it's dividing. How will I move it over? So you're saying I'm going to have a, come on, pen. I'm going to have a 2 and a D. I agree. What's the A doing to the T? So how will I move it over? Now that's going to give me this, T squared. How do I get rid of squared? The other side. By the way, a common mistake, we haven't gone over the acceleration test yet. We will when I have a short lesson. A common mistake I saw, kids were square rooting whenever there was a t in the equation, even though they weren't getting the t by itself. So there was a question on your test where I said find a using this, and I saw people square rooting the a. No, you're only square rooting here because you got a t squared by itself. How do I get rid of a squared? So t is going to be the square root of 2 times negative 4.5 divided by negative 9.8. I think it's going to be a little less or a little more than a second, little less than a second, is it? You're not in free fall for very long because I tried to make this survivable. I didn't want to kill your brother, at least not at that time. 2 times negative 4.5 divided by negative 9.8. Square root of that. 9.58, I'll carry a few extra sig figs because I'm going to use this. So I'll go 0.9583, even though if I was giving this, I really should only go to 2 sig figs. I want to use this. 0.9583. Okay. B. What's B asking me to find? Isn't VF 0? No, not when he hits the water. When he gets to the bottom of the water, yeah. But when he hits the water, I guess it wants us to find VF. I got a couple of choices. I could use VF squared equals VI squared plus 2AD. That would be using all the data that they gave me, Chris. But what else did we find in part A? What else do we find in part A? Time. I think we're good enough. You gonna make it, Josh? You're not looking good. You sure? Nah, I don't think so. You know what? It's a team effort. So, Chris, I could use that, but because I found T, and I think now we're confident enough that we can use something that we found to find something else, I think I'm gonna, instead of using that, I'm gonna use VF equals VI plus AT, where VI was 0, A was negative 9.8, and T was 0.9583, although I'm gonna use my answer button right there, because I wanna be really accurate. Do I need to go 0 plus, or will that change the equation? So I'll write it, because just to let myself know, but I'm just going to go negative 9.8 times answer button. Looks like the impact velocity when he hits the water, negative 9.39 meters per second. What's the negative telling me? He's going down. Okay. Turn the page. Cross out the word pool, lake. I did say cliff jumping. It started out as a diving board question, then I went back and I changed it to make it a cliff because it sounded more interesting, but I forgot to change the second part of the question. So if Regan's feet just barely touched the bottom of the lake, which has a depth of 2.5 meters, what was his average acceleration while he was in the water? Okay. What's this question asking me to find? Acceleration. And I think because they're giving me distances and I just did a bunch of VI, I think I'm still not using forces to find the acceleration. I think I'm going to use last unit. Yes? So I'm going to write down A equals question mark. What else do I know? I guess negative? It depends where we start looking from. If we're looking from the top of the water, then is the lake below him, or is the bottom of the lake below him or above him? I guess we should call that negative. Oh, they don't need to tell me this. What's V final whenever you jump into water? for a split second, right? You come to a stop, and then you start going up again, but we're not worried about that. You come to a stop. What was V initial when he hit the water? V final when he was in free fall. That's why I was so careful last time. What did we say it was? Negative 9.39. I'm looking for an equation that has a, I can't use T because T was during free fall. It would take, in fact, I suspect it takes them longer to come to a stop in the water because water's thicker than air. I'm looking for an equation that has A, D, VF, and VI in it. VF squared equals VI squared plus 280. I'm tempted to hit Brad again, but I've been picking on him all day. Hey, let's get the A by itself then. How would I get the A by itself from VF squared equals VI squared plus 2AD? Eric, you preach it. It's going to be 0 squared minus, and I got to be careful, negative 9.39 squared. And I'll put the negative inside brackets and the squared outside brackets. Or you know what? Wait. What's a negative squared? You know what? On my calculator, I won't bother typing that little negative right there because it's a waste of time. It's going to cancel anyways. Yes? All over 2 times negative 2.5. More than one number on the top, more than one number on the bottom, so brackets. In fact, you know what? What's 0 squared? 0. I'm not going to put the squared on the 0 either. 0 minus 9.39 squared. Again, I chucked the negative, Olivia, because I knew it was going to cancel inside the brackets, but there's still a minus sign in front, right? Divided by 2 times negative 2.5. What's the acceleration? 17.63. 17.6, let's say. What direction? Positive means what? Positive means what? What direction? Yeah, up, of course, because you're slowing, you were going down, but you're slowing down. That must mean you're accelerating upwards. That's what the water does. And it gives you about somewhere between 1 and 2 Gs. This is about accurate. This is why, Dom, it hurts to belly flop. Okay? But if you're tucked, you go down much further, you'd go much longer. That's not too bad. If you belly flop, you come to a stop so much quicker. This distance is so much smaller. The acceleration is so much more. That's why it hurts. Okay?
Have you seen the world record holder for like the longest jump into the pool?
Probably, but if you have a video, send me the link. But I got to finish this lesson. Okay? Oh, I'm sure. Chris, what's D asking me to find?
The net force.
Ooh. What is the net force that the water exerted on him? Well, net force equals MA. And I guess the net force of the water would be MA water. Do I know his mass? I think I said it on the previous page, didn't I? 65. Do I know the acceleration from the water? Hey, that's what I just figured out. 65 times 17.6 times 65, 1,150 newtons. Last one. Draw a free body diagram, it says, for the forces acting on a book sitting on a table. So for all of you, it can be your binders that are sitting in front of you. Represent your binder with a dot. What are the forces acting on your binders? Get the obvious one. Gravity. Is your binder sinking into the table like quicksand? Is it lifting into the air like Superman? So there must be an equal balance force in the opposite direction. What force? What's exerting the force? The table. That's why if that table magically vanished, suddenly it would accelerate again. If we had somehow, genie powers and said, boom, made the table vanish. So F, table. We're going to give that force a special name next class, but for now we'll call it force table. I think that's it. Those are the forces acting on your binder. Got a video to show you in a second, but what's your homework? Some of these are still going to be tricky. In particular, number 1, I will happily go over next class. It's about a half step beyond what I've done with you, but I'm curious to see which of you, by looking at the answer, can puzzle this out, can figure this out. Your hint is draw a good free body diagram and see if you can puzzle it out. So number 1 says we have a 2-kilogram rock attached to a rope. It's pulled. Write a net force equation, A if it's accelerating up, B if it's accelerating down, and then find the cord tension, and it gives you different accelerations. See if you can figure those out. Number 2. This one is tricky because this is the tricky one. I'm giving you the tension, and I'm saying find the acceleration. In fact, you might have some trouble, but I'm curious. Number 3, this one is algebraic. This is tricky. Again, I'm totally prepared to go over this next class, but I'm always curious to see who can figure this out on their own. Skip 4. Number 5. All of you right now underline the phrase constant speed. And my hint for you is do a good free body diagram. This free body diagram will have some sideways forces in it too, I think. Number 7. And number 9 is very, very similar to the Regan cliff jumping, except here instead we're having a mountain climber coming to the end of a safety rope. This is also a tricky one. In fact, I give this same question with different numbers to my Physics 12s, and they struggle with it. So the message I have for you, try all of these. If you're stuck, try looking at the answer and see if you can reason it out, but I'm totally prepared to go over these with you next class if I need to. Got one more cool video. So we've been talking